classification of forces and moments acting on a ship during its motion and roll. This is article number 12.1 from the book Mechanical Systems Calculations of the Marine Facilities. To consider ship motion in the water, to study it, the rolling or the motion under controls, first of all is the general show, the theoretical show of definition of the coordinate system. So it's important for this issue to determine the elements of the ship motion in the water. So we have the scheme of the coordinate planes on the figure 12.1. We have here three planes. First, the main plane. Main plane is horizontal one passing on bottom of the ship. The diametral plane is a vertical plane, longitudinal. Diametral plane, the plane of the symmetry of ship sides. This usually, if we assume the ship symmetric, this is usual. And the midship plane, the transverse plane, in the transverse vertical passing the middle ship waterline lengths in the middle of the waterline. This is usually usual location of the planes. And when the planes of the ship, considered planes, intersect, we thus determine the Cartesian coordinate system axis. So what can be the axis used to find the elements of the ship motion, like ship rolling or motion under controls? First, associated with the ship Cartesian system of the coordinate. So the abscissa axis directed to the bow of the ship, the coordinate axis directed on the left, and the applied axis directed upwards from the same point, the point of the intersection of three planes, of the main plane, of the diametral plane, and of the midship plane. So this is a right-handed system of coordinates. How determine? If one rotates the abscissa axis toward ordinate axis, and when we associate the right crew with the axis, with the coordinate systems, so the direction of the motion of right crew when rotating abscissa axis to ordinate axis will be the applied axis. The direction of the motion of the right crew when rotating counterclockwise, watching towards the direction of applied axis. This direction of motion of the crew coincides with the direction of applied axis. This is a right coordinate system. Sometimes in the issues of ship, for example, for the rolling of ship, likely used the left-handed coordinate system. This is when rotate the abscissa axis to the ordinate axis, and if we have the associated left crew, it will move along the applied axis. All those applied axis is vertical, so for the left coordinate system, the ordinate axis have to be directed to starboard. For the right-handed system of coordinates, ordinate axis directed to port side. So, and what kinds of the coordinate systems Cartesian we used for this issues of determination of the ship motion when rocking and when moving under control? The first is associated with the ship right Cartesian system of coordinate, which, for example, is indicated is performed on the figure 12.1. Second, moving coordinate system G, X, Y, Z, a moving coordinate system, those whose the center of the moving coordinate system coincide associated with the ship, and a fixed coordinate system as well. We have 0, 0, Xi, eta, zeta. the origin of the fixed coordinate system associated with the same as the moving coordinate system with the ship mass center at the initial moment of time. Although this coordinate system we say geographical, so it remains, and the ship moves in the fixed coordinate system. And the force is a semi-coupled coordinate system as G, zeta X1, eta 1, zeta 1, the axes of which are parallel to axis of the fixed coordinate system, and the origin is associated with the moving center of the mass of the ship. All the coordinate systems to research the ship motion and to find elements of motion, to find the acting forces. All coordinate systems are inertial, so we can determine in each of the coordinate systems, for example, with associated with the ship coordinate system, we can determine the accelerations. It can be the longitudinal acceleration along the x-axis, in the general approach, longitudinal acceleration, transverse acceleration along y-axis, and vertical acceleration along z-axis, and as well the rotational acceleration of the ship heeling, of the ship trimming, and of the ship yaw. So rotation around the applied axis yaw. So finding the elements of the ship acceleration in any coordinate system, we next can determine the forces of the inertia, and we can decide the differential equation of the ship motion. The accelerations are the second derivative as known of the displacement. The displacement in the coordinate systems, for example, the moving coordinate system or the associated with the ship right Cartesian coordinate system, the accelerations are the displacement are the displacement along x-axis, just the ship motion along x-axis, the horizontal rocking of ship, or just the motion at the controls in the transverse direction. It will be the transverse direction along y-axis, coordinates, and the vertical rocking of ship along x-axis, as well the rolling of the ship, the rolling of the ship around by the axis x, abscissa, rolling. This is like a rolling heeling. The rolling around y-axis, ordinate axis is trimming, and the rolling around applied axis, this yaw. We thus have to consider three elements, 6 elements of the motions, as she, eta, and zeta identical with axis, and the 3 angular motions, the roll angle, theta, the rotational ship relating to abscissa longitudinal, gx, the trim angle, phi, the rotation related to the ordinate axis, gy, and the yaw angle, chi, the rotation around the axis of the applied axis, considered the components of the single vector. So we consider 6 components of in the most general approach of the ship motion in the coordinate system, as we have the motion of ship along the three translational motions, she, eta, zeta, and 3 angular motions, heel and theta, trimming phi, and yaw chi. Despite the fact that 3 of these displacements are linear and or translational, and 3 angular, due to in the derivative equations, when we have to decide to find the elements of the ship motion in the coordinate system, the formal approach is equal as for the translational motions of ship, so as well for the angular motions. Besides all the indicated coordinates of components of single vector of the ship location in the coordinate system, we have to indicate other elements of ship motion on the surface of water. This is a drift angle, BD, between the velocity vector and abscissa of the axis. The curvature of the trajectory, the linear velocity of the certain point on the weighted surface of hull of the ship. The course of the ship, that is the angle between associated longitudinal axis and the abscissa axis of fixed coordinate system, zero ship. With the maritime navigation, this course defined relative the direction to the north. And the velocity angle, that is the angle between the direction of ship velocity vector and the abscissa axis of the fixed coordinate system, zero she, abscissa axis. The relationship between the course of the ship on water surface and velocity angle and the drift angle, the relationship indicated here by the formula. So velocity angle equal to the course total with the drift angle between velocity vector and abscissa axis. Classification of forces and moments acting on the ship. When determining rolling elements, it's a little bit different, the classification of force and moment when we determine rolling element of ships and the ship motion and the controls. When determining rolling elements of ship, the forces we consider usually four categories. The first category is the internal force and moment caused by the massiveness of the ship in the water. And these forces are proportional to accelerations. The damping forces and moments of resistance during translational motion and the rotation caused by the viscosity and massiveness of water. The cause as the massiveness of water mean that the energy dissipated by wave generated by moving ship. And the third category, the restoring forces and moment depending on translational and angular motions and returning ship to equilibrium position. This is not for all kinds of the ship motion. Sometimes, for example, for longitudinal ship motion along the abscissa axis and for transverse ship motion along the ordinate axis and for yaw, the rotation relative the applicate axis, we do not have the restoring forces due to no forces return the ship in the position of the equilibrium relative to this axis. Only we have the restoring forces when the ship have to be returned to the equilibrium. If the ship is stable, considering the ship stability on surface under the heeling, and considering the ship stability due to the keep the water line level of the water line, and the draft of ship has to be stable if the ship do not flooded by the water. And for these forces, as well for heeling, for vertical rocking, and for the trimming of the ship, for pitching, for these three kinds of rocking of ship, we have the restoring forces and moments. So probably more correct to say that this is not the forces only, but the efforts. Due to some of the forces are the moments. Formally, the operations over forces and moments are the same when finding the element of the ship rocking or motion under controls. And the fourth category, disturbing forces and moments, deviation ship from the equilibrium position. For example, the forces and moments of wave nature. Yes, sometimes ship heeling, pitching, and vertical rocking depends on the waves. The peculiarity classification of force and moments in the issues of ship controllability. Yes, when considering the ship under controls, we have a little bit other classification of ship, of the forces action on the ship. The issues of the on ship controllability, the following classification of action force and moments into categories are common. The first category is driving force and moment, the control efforts generated by ship propulsors and controls. Ship propulsors generate the forces in the longitudinal direction, for example. If we consider the ship propulsors as the control over the element of the ship longitudinal motion, for example, over the velocity control. Usually we consider the rudders as the controls of the ship. The forces caused by the rudders are driving forces too. Second category is external forces and moments, which sources are in the aquatic environment, don't have a causal dependence on ship motion. Third category, reactive forces and moments from water environment rising by the ship motion. And the reactive forces and moments acting on the moving ship from the side of the water environment. In turn, we can subdivide into the following categories. First category, the inertial proportional, the accelerations of translational and angular to masses and moments of inertia, and the viscous ones proportional to velocities, translational or angular, or the squares of velocities projections. I have to underline that usually to determine the elements of the ship motion in the water by decision of the differential equations is adopted the hypothesis of the linearity, that is assumed the damping forces assumed proportional to the linear degree of on the velocities, not to the square degree. As in hydrodynamics, probably this more characteristic to consider that the hydrodynamic forces can be proportional to the squares velocities. But the hypothesis of linearity required to have the analytical decision of the differential equations. So the viscous ones proportional to velocities, translational and angular. Viscous, the category of directive forces, viscous, or to the squares of the velocities, but likely to the velocities in the fourth degree. The reactive forces are damping. Or the positional forces, the second category of reactive forces and moments acting during translational motion, and the damping ones arising during rotation. So can be inertial forces, reactive, and the positional forces. The indication of the proportionality coefficient in the equations of ship motion. The proportionality coefficients between inertial force and moments on one hand and the translational angular accelerations of ship in the water on one hand includes the ship displacement, the moments of inertia of ship relative to coordinate axis, the moments of inertia relative axis of abscissa axis, coordinate axis, and the applicata axis YZ, IZ. And besides, the characteristics of inertia are the added masses on the moment of the inertia, these characteristics of the impact of water on the inertia of ship when it moves in the water. We indicate like the mu, I, J, and the indexes from 1 to 6 accordance to is the most general approach in accordance with the degrees of freedom of the ship in this space. Let me first of all show that just matrix, how it looks like. It looks like that. So we have the diagonal matrix of the characteristics or own characteristics of the inertia of ship, as this is ship displacement delta uppercase and the moment of the inertia of ship around the abscissa axis, moment of inertia around the applicate axis, and moment of the inertia around the ordinate axis and the applicate axis. And besides, we have the matrix of factors of the added masses of water. So how does this water environment impacts the characteristics of inertia of the ship, just itself ship? And we have the factors like indicated 1, 1, 1, 2, etc. The row in the matrix and the columns 1, 2, 3, 4, 5, etc. So what is it? This is added mass of water in the ship motion, impacting the forces of the inertia in of ship in the motion along the abscissa axis 1, characteristic 1 abscissa axis, translational motion. So displacements are characteristics of the inertia of ship in the translational motion, and the moments of the inertia, characteristics of the ship inertia in rotational motion. And this indicates the first index, in what direction we consider the impact of the inertia of ship on behalf of water. And the second index means in what direction motion ship with acceleration caused by the force rising in the forced acceleration, on the forced acceleration. This is how do the ship transverse direction motion impacts on its inertia in the force direction. How do the ship heeling around abscissa axis impact the force direction longitudinal? The inertia of ship characteristics in the longitudinal direction, and this how do the ship motion, angular motion around the coordinate axis, the streaming impacts the inertia of ship in the motion along the abscissa axis, etc. And how do the ship yaw rotation around the applied axis impacts on the ratio in the water, in the ship motion and translational motion along the abscissa axis. So this is a more general approach. It could be subject of some simplification. And indices corresponding to the translational motions, velocities, accelerations in direction of axis abscissa ordinata applicata are 1, 2, 3, or 1, 2, 3, and two angular moments, angular velocities, angular accelerations under rotation relative to axis abscissa ordinata applicata, accordingly 4, 5, 6, or j equal to 4, 5, 6. So y is index in what direction we determine the forces of the ship inertia. And the second index, this I, characteristics, in what direction we consider the ship inertia force or moment, just inertia efforts arising when the ship moves with the acceleration. And the second, 1, 2, 3, J, or J, 4, 5, 6, from what direction motion we consider the appearance of the force of moment, that is the effort of the inertia, in the considered motion indicated I. So this is the indication J of the motion, which is the source of the force, and I is the direction in what I 1, 2, 3, 1, 2, 3, in what direction we consider the force or moment arising under the action of the second one motion. And we are talking about the inertial motion. That is, we are talking about the factors of the proportionality between the acceleration in the direction J. 1, 2, 3, J is a translational acceleration along the axis of the inertial system of coordinate Cartesian. And 4, 5, 6, that is the angular directions of the acceleration of the ship rolling and the yaw trimming relative to the system of Cartesian system of the coordinates. And this is the direction in what the force arises, consequently due to the motion in the J direction. And the factors in the proportionality of this means the water impact, mu of the yj, we say. The first index denotes the projections of components of the inertial force on axis abscissa, ordinata, and applicata, or the projections of moment of the inertial force during rotation and acceleration, with acceleration relative to the axis abscissa, ordinata, and applicata as well. The set of damping coefficients as well we have to consider, because besides of the forces of the inertia, we have the forces of the resistance, usually proportional, assuming the hypothesis of linearization of the dependence of the forces of the resistance on the velocities. We assume that perhaps with small velocities, we can assume that the forces of the resistance are dependent on the velocities linearly. In this case, we have to use the damping coefficients with the same system of the indication. So ij as a moments of the inertia on behalf of the water. The damping coefficients, the first index I mean, in what direction we consider, and we are looking for to find the force of resistance, and J is what direction is the motion relative 6 degrees of freedom of the Cartesian coordinate system, 3 translational and 3 rotational. From what J direction we consider the impact on the resistance force in y direction. And this is a factor of the proportionality between the velocity and the rising force. The system of related equations of motion during roll covering the projections of forces and moments. This is a matrix form of the sum of projection of forces and moments. This is a total of projections. R is matrix of the inertial forces. These arguments of matrix. Arguments are the own characteristics of the ship inertia and the edit mass of the water characteristic of inertia. Some of them are just masses of ship, just like displacement, for example. And some could be the edit masses, could be the edit masses. So the factor of the increase of the inertial ship when it moves with the acceleration in the water environment, other than with not water. And some of the argument like M is the moments of the inertia. So due to accelerations angular, the factor of the increase of the moments of inertia of the inertial nature. This is moments of inertia of edit moments of the inertia of water. And this is second derivative of the coordinate. The coordinates we have 6. The 3 translational coordinates of the ship motion translationally are in the Cartesian coordinate system, inertial coordinate system, in which we consider the impact of the acceleration onto the inertial forces and moments. And the 3, that means the I is 4, 5, 6, the angular accelerations. So second category is damping forces. The arguments are the matrix of the damping coefficients. This matrix of damping coefficients as well. This matrix of damping coefficients and the edit masses coefficient, the factors of the proportionality of the forces and moments arising when the ship moves with acceleration in the water environment. This matrix system are symmetrical due to the diagonal, the matrix. So mu1, 2 equal to mu2, 1, mu3, 1 equal to mu1, 3, etc. Symmetrical due to the diagonal of the matrix. The same, the matrix of the damping coefficients, the factors of the proportionality between the ship velocity, considering the hypothesis of linearization of the ship dependence of the forces of resistance on the ship velocity in the water. And this is a factor of the proportionality. This matrix of the factors of the proportionality indicates, each of the element indicates of this matrix in what direction first. For example, could be in first direction we have to determine, we are determining the force of the resistance, and the second indicates in what direction we consider the velocity impacting the force of resistance appropriate to the first index. So this, for example, is the impact on the vertical motion of ship, force of the resistance due to vertical motion under the ship motion angular relative coordinate axis. So trimming, how do trimming impacts the vertical ship motion, that's maybe vertical rocking. This is a factor of the proportion between the velocity in the second index direction due to the force arising in the first index direction. This is the coefficient of the proportionality. And this matrix, as well as the matrix of the added masses, are symmetric relative the diagonal. So these elements are reciprocal. Lambda 1, 4 equal to lambda 4, 1. Lambda 6, 2 equal to lambda 2, 6, the factors of the damping. And the matrix of restorative forces we consider as well. The matrix usually is a dependence of the listed arguments, like this is the displacement of ship, the mass of the ship. And this is the initial metacentric cage for the ship Helen. What's that? This is a vertical distance between the center of ship gravity location and the point of center of ship rotation when Helen. So this vertical distance equivalent to the transverse initial metacentric cage. And this is longitudinal metacentric cage, initial metacentric cage, longitudinal h phi. This is a distance between the ship point of gravity and the location of the center of ship rotation when it trims. So xw is the longitudinal location from the reference point of the coordinate system to the point of the center of area of the water line. So the horizontal section of ship hull by the water line characterizes the location of the center of the area of the water line, this abscissa of center of the area, this ordinate of center of the area of the water line, if we assume the ship symmetric, and if the system coordinate reference point located on the plane of symmetry of ship, yw equal to 0, SW is the area of the water line, and x is the vector, but not the second derivative, like finding the inertia forces, and not the fourth derivative as we find the resistance or damping forces, assuming as well the hypothesis of the linearization that the damping force depends on the velocities in the first degree. The restoring forces usually correspond the displacement itself. It could be the translational displacement, for example, vertical displacement translational along the applied axis, and it could be the angular displacement along the abscissa axis. This would be Helen, and the ordinate axis, that would be trimming of the ship. And the ship coordinates vector as well used in this the argument, and this is the functions on time, and this is the first derivative to find the damping forces, and this is the second derivative to find the forces of the inertia. So here she is the displacement of ship along the abscissa axis. Это is the translational displacement of ship along the ordinate axis. This zeta is applicata of the translational motion of ship. Theta is angle of ship Helen relative the abscissa axis. Phi is the trimming angle of ship relative ordinate axis, and chi is the ship angle of yaw relative applied axis. The vectors of time derivatives coordinates, the derivatives of this vector, it is the time derivative of each component of vector, and this one second derivative. The magnitude, we just listed the arguments of this function within a matrix form of the equations of all forces total as a balance equation for the ship to find the elements of its motion. The ship waterline area indicated, and the metacentric cage distances between the points of the gravity to the center point of the ship motion when rotating in the longitudinal plane diametric that is rotating relative ordinate axis and the rotating of ship h5 relative h5, excuse me, the rotating relative the ordinate axis, and h just rotating around the abscissa axis, that is the heel, and this is trim and rotating. Ship abscissa and ordinate of the center of the waterline area x, w, and y, w. Y, w could be 0 if the ship is symmetric. Sometimes we assume that ship symmetricity not only relative the diametric plane, but we can assume sometimes the ship symmetry relative the midship plane. If a ship is symmetric relative the midship plane, x, w will be equal to 0, 2. And the matrices we consider as well the own masses and moments of ship inertia, own masses and moments of ship inertia, m with a star index, and the added masses of damping, added masses, and the damping matrices. So this is matrices in the equation. The matrix of the own inertial characteristics of ship, m, this is a stroke, Astor stroke has a diagonal form. Diagonal form, and these two matrices are symmetric relative to main diagonal. The restoring and disturbing forces are vectors and have the form the restoring forces. We do not have the restoring forces along the translational motion along the abscissa axis and ordinate axis for the Cartesian coordinate system associated with the ship, and relative the for the rotation moment in the plane of the ocean, the plane of the water surface, relative applicate abscissa. So we don't have restoring forces. No restoring forces we have when the ship when we consider the vertical rocking of ships, that is the periodic motions relative the periodic translational motion relative the applicate axis, vertical, and two rotational motions for the ship relative to the longitudinal axis, that is ship heel and the relative the ship, and relative ordinate axis, that is the forces rotating ship, disturbing forces, excuse me, restoring forces, returning the ship in the position of the equilibrium. In the ship, rocking relative the ordinate axis y, angular displacement. So, and we have three main types of ship rocking. This is vertical rocking. This is number 3, vertical rocking, for which we have the main types of ship rocking are those which associated with the directions for which the restoring forces are characteristic. And the second is the second main is trimming of the ship, pitching, and next is the ship, excuse me, V5. This is restoring forces for ship pitching. V4 is restoring forces for ship rolling, and V3 is restoring forces for ship vertical rocking. And besides, we can have 6 disturbing forces. This is linear disturbing forces. This is moments. This probably would be more correct to say the disturbing efforts. Just 3 of them are not forces, but the moments. And we have the matrix notation of the system of equations in the shows of ship rolling. This looks like not only rolling, but as well the control motion. This looks like the bracket in the brackets, the total of 2 matrices. This one with the asterisk, and this is second plus m, the added masses, and the product by second derivative of the vector of the ship motions. And plus the second summand is the matrix of the damping factors, damping coefficients, product by the force derivative of the vector of the ship motions, and plus the restoring forces, and equal to the disturbing forces, general form of the equations of the ship motion in the water environment. This is a open form of these equations. The last one equation look like that in the most general approach. Yeah, after that we can do some simplifications. Please see the first is the equation of the ship motion along the longitudinal axis. That is, axis number 1 is abscissa axis. So this is the force of the inertia of the first row is 1, 2, 3, 4, 5, 6 summons. 6 summons mean the inertia forces arises when ship arises along the abscissa axis on behalf of the accelerations all of the axis. So this is the acceleration, the relative the longitudinal acceleration, just translational of the she of the motion along the abscissa axis. This we consider in the inertial systems of the coordinates. That is what the acceleration we can define as well in the system coordinate, which moves together with the ship. So despite the fact that the system of coordinates are moving associated with the ship, that is, we consider the acceleration of the system of coordinate. And the second summand, the factor of the inertia of the ship in the longitudinal direction when it moves along with acceleration along the abscissa axis, but this factor, these forces as this product arises due to the ship transverse motion. So as the ship motion and the transverse along the ordinate axis with acceleration impacts the forces arising in the first direction, that is the forces arising in the direction of abscissa axis. This is the forces arising along the abscissa axis under the impact of the acceleration along this is zeta second derivative by time the acceleration along the applicate axis, and this is the force arises, the force of inertia arising along the abscissa axis and the action of the acceleration phi theta second derivative, acceleration of the ship rolling, this acceleration of the ship pitching, this acceleration of the ship yaw, and this is all factors indicate that all summons respond to the inertial forces arising along the abscissa axis on behalf of all these factors of all other direction of the ship motion with acceleration. The second row, we have the damping forces, that is the forces of the resistance. The same indication, this is lambda is a factor of the proportionality of the force of resistance, which appears along the abscissa axis on behalf of the velocity of the ship along the same axis. This is the force of resistance arising along the abscissa axis, and the cause of the velocity of the ship along the ordinate axis, this motion, the ship along the vertical motion along the applicate axis. This is the velocity, first derivative of zeta, and this is the first derivative of pitching, first derivative of yaw, that is the all velocities, and the factors indicate that the force of resistance rise in the first direction, and the impact of the velocity of the ship of the definite one direction of the second index in the lambda indexation plus 0. 0 is absence in the longitudinal direction of the restoring force and equal to the forces of disturbance. Disturbance the force which external forces. The second equation we have, we can see that only two rows of this equation as the second two rows as well, and the last one is the not the main types of the ship rolling. That is, if we have three rows in the equation for third direction, for third equation, fourth and fifth, that is the equations for the main types of the rolling, of the ship rocking, What is the difference? The difference is that the third row is restoring force. For example, here, this is restoring force for the vertical ship rocking is consists of the force arising in the vertical direction. For example, the first one is dependent on the not the derivative, but on the element of the ship motion on the definite axis itself. So the force arising in the vertical direction along the applied axis when the ship moves in the vertical direction proportional to this is the weight, the mass density of water, equivalent usually 1.025 ton per cubic meter. This is gravity acceleration 9.81 meter per square second. This is the area of the water line. So when the ship is moving vertical, this along the applied axis, the volume entering in water or when which goes out of the water proportional to this displacement of ship and the area of the water line. This is how much we submerge ship or we take it out of the water. If we, this is a volume characteristic. So change in volume characteristics proportional to the ship displacement along the vertical axis zeta. And when we find the product of the submersion or emerging volume when the ship experiences the vertical rocking, so we multiply this volume onto the water density, mass density, and multiply by the gravity acceleration, we can find the force. The extra force which varies in dependence on the ship displacement when it moves vertical along the applied axis. The second is the same, but this is product of the ship displacement by the gravity acceleration, by the metacentric edge, and by the angle of the ship heeling. This total mean that this is the healing, the moment, restoring moment, restoring moment. So as the ship we consider as a stable, so the metacentric edge is more than zero. So the point of the gravity of the ship located below relative to the point of the center of ship rotation when it rolling. So the if the, in this case the ship we consider stable. In this case, this product of the metacentric edge by assuming the smallness of the theta. Theta is the angle of the ship heeling when rolling. This is a product. This is the arm of the restoring force. Arm of the restoring force displacement multiplied by the gravity acceleration of the ship weight. This is mass. This is weight. The weight is the force is a product of the mass by the acceleration and this arm. So this is a restoring moment. If you divide the restoring moment by the ship location in the transverse direction of the point of center of the center point of the ship of the area of the ship waterline. That's why we can find the extra force which arises when which impacts the restoring force with the deviation from the symmetry of the ship. The restoring force arises in the direction of the vertical rocking due to the ship motion in the direction of the rolling. And this is a ship, the force is the moment arising when the ship pitching. When we divide to the abscissa, so we can find how does it impacts on the force restoring the ship in the longitudinal direction. So, and equal to disturbing force. So this is the just explaining in the most general approach what forces acts on the ship proportional to the second derivative of definite one displacement, and the each equation corresponds to the total of the forces, or maybe in the moments, just could be said the efforts on any of the axes of coordinate system, 6-dimensional, 3 linear, and 3 angular, and consists of the forces of the inertial proportional to the squared to proportional to second degree derivatives, forces of resistance proportional to fourth degree derivative, and proportion to the ship dimensions itself. And next we can just simplify these equations. If we assume the ship symmetry, so we can consider all kinds of the ship motion independent. So in this case, we consider, and we will consider only the main kinds of ship rocking. For example, we consider the vertical rocking, we consider the ship rolling the rotation around the longitudinal axis, and we consider the ship pitching the rotation, the rolling around the ordinate axis transverse. So this is the main kinds of the ship rocking. Due to these kinds of rocking and projections have the restoring forces. We consider only this, and we can neglect the impact of definite summons, because if these summons are, because due to the assuming the property of ship symmetry, so some summons have to be equal to 0. And in this case, we can simplify this considered system of the second order differential equations linear of the ship motion in the water in the 3 dimensions of the translational motion and 3-dimensional gravitational motion. We can reduce this only to 3 equations. One equation is the equation of the ship translation motion along the applied axis, and 2 equations of the rotational motion around the abscissa axis, that is the Hillen, this is the pitching, and all these 3 is inhomogeneous linear second order derivative equations. And we can have the decisions for the homogeneous equation of ship rolling in calm water. In calm water, we equated the disturbing forces and moments on the right of the equations to zeros. And after mathematical transform of these mathematical equations, we can have the decisions of this equation. First of all, we transform the equations to the indicated form. To do that, we have to divide both sides of the equation for the first one factor. For the first one factor, and we will redefine the indexes, redefine the notions of the equation. For example, for the second, we consider the factor 2 multiplied by this nu 3. Nu 3 is a decrement of the vertical rocking damping, this decrement, and nu 3 is a decrement of vertical rocking damping. This we got as we divide the lambda by this factor, the damping coefficient by the characteristic of the ship inertia, the displacement of the ship due to the vertical motion and the added mass of the water in the vertical motion of ship. And we will have the damping decrement. Accordingly, by this formula, we substituted here. And besides, we can have the natural frequency of the ship vertical rocking. This frequency squared, and we can find this frequency as the fraction. In the numerator, we have the water density and the gravity acceleration, the area of the waterline of the ship, and in the denominator, we have total of the ship displacement and the added mass of water in the ship vertical motion. This all under assume got from the matrix assignment of the equations of the ship ocean the water, considering the matrix forms of the own characteristic of ship and the added masses of water and the factors of damping here, and the dependence on the second derivative and the first derivative of the elements of the ship motion in the water. This is elements of the ship motion water, she, eta, zeta, the theta, the phi chi is the yaw, pitching, rolling, vertical, rocking, transverse rocking, longitudinal rocking. That's what the fourth and the fifth we consider the main kinds of the ship rolling due to for this third equation, fourth and fifth, we have just restoring forces and no forces or moments restoring the ship to the original position in the ship rolling, in the ship rocking along the longitudinal axis and transverse axis, abscissa ordinata, and when rolling, when yaw rolling around the applicat axis. So we consider the main types of rolling, the vertical rock and the rolling and the pitching of the ship. And after a definite transform, assuming the ship symmetry, we consider these types of the ship, the main types of the ship rocking independent on other three types, and we can just do the simplification relative to the factors in this matrices of the added masses and the matrices, masses and the damping coefficient. Due to the assumption of ship symmetry, this matrix became the diagonal 2, and we consider only third, fourth, and fifth as for first, second, and six rows of the matrices. This fourth, second, and the six are not the main kind of the ship rocking, as we do not consider for these kinds for the horizontal displacement of ship, to the transverse displacement, to the angular displacement around the vertical axis. We do not have the efforts restoring the ship in the original location. And to find the natural velocities after all these assumptions, we found that we have three homogeneous second order linear differential equations with the factors nu 3, nu 4, the same system of the indexes. This means that nu is mean the ship rocking decrement is due to the damping of the ship rocking. And omega 3 squared, omega 4 squared, omega 5 squared is the natural velocities of ship vertical rocking, natural velocity of the ship rolling, natural velocity of the ship pitching. So we can find this all as derivatives. In the first, we have the characteristic of the restoring force for the to find the natural velocity, this restoring force for the vertical motion of ship, which removes the ship to the balance position to the water line. This is the moment. Moment is the weight of ship delta product by gravity acceleration, and this characteristic of the metacentric H. If we product this all to those assumed small angle of the ship rolling, the heel angle, we will have the moment restoring the ship in the balanced position. The same for the ship pitching, but we have another one metacentric H. This is longitudinal metacentric H, and this is transverse metacentric H, the distance between the ship point of gravity and the point of location of and the point of rotation, point of gravity and the point of rotation of ship when it rolling around the longitudinal axis, and this is the longitudinal metacentric H, that is the distance between the point of ship gravity and the point, the center of the ship rotation when pitching. And finally, we have the decrements of the damping of the vertical rocking of the rolling on the pitching. This is the main kinds of the rolling. For this only we have the restoring forces. Restoring forces caused the third summons in each of the equation. This second summand characterizes the damping forces, and the first summand summons came from the forces of the inertia. Forces of inertia here in the determination of the natural frequencies for the ship vertical rocking, for the ship rolling, for the ship pitching, the characteristic of inertia are their own moments of the inertia, relative abscissa axis, relative ordinate axis, for example, and edit mass relative the same axis, relative mass. We use only one index due to these simplified equations. So we consider only the impact on definite impact of the force appears for each definite direction under the displacement or velocity of the first derivative or displacement or second derivative of the acceleration in the same one direction. So we don't need the second index there here. And thus we reduce the general system of the ship motion in the water environment to the simple form of the linear second order homogeneous for the rolling on calm water equations. And we can have the decisions of equations. This is a type of the decisions. This is the water, the rolling with the resistance. That's why we have not only the cosine factor, cosine function of ship rolling and the amplitude of ship rolling depending on the initial conditions to find the amplitudes, to find the phases, initial phases, B3, B4, B5. We have all amplitudes, zeta 0, theta 0, and phi 0. We have to have the initial, this is second order equation. So we have to have two for each a couple of constant. We have to have the two initial conditions for definite time period of the, or maybe the initial amplitude or initial velocity or initial acceleration. So two of that, or amplitude or velocity or acceleration for definite time period. And this is the decisions of simplified equations of the ship motion in the water, considering as well the characteristics of inertia and damping on behalf of the water environment. Yes, and the questions and comments. The coordinate systems for finding the elements of pitching and controlled motion of ship. We have the moving coordinate system connected with the moving ship, in which it is convenient to find the forces acting on the ship. We have the system of origin. The axis directions are corresponded with the ship motion in water. This is a moving coordinate system. The fixed coordinate system, the so-called geographic coordinate system, in which it is possible to determine the motion of ship at the initial moment of moving coordinate system, may coincide with the fixed one. The semi-connected coordinate system, which origin is associated with the moving ship and the axes are parallel to ones, in the fixed coordinate system. Now, this is just explaining about the coordinate systems. Coordinate systems are the lines of the intersection of the main planes. Main planes is the base plane, the diameter plane for the symmetric ship, diametral plane, and the midship plane, transverse vertical plane, and the midship. 12.1.2 directions of axis of Cartesian right-hand coordinate system determined by rule of right screw. When the abscissa axis is rotated relative to the applied axis, the direction of the coordinate 1, the rotating right screw, which axis coincides with the applied one, moves in the direction of the applied axis. Otherwise, the coordinate system is left, and the left screw fixed with x-axis rotating towards y1 moves to the direction of the applied axis. That's why. Now, sometimes we use the left coordinate system. The left coordinate system, the abscissa axis directed to the ship bow, the coordinate axis, for the left coordinate system directed to starboard, and the applied axis directed upward. So, for example, the left coordinate system we usually use to decide the mathematical equation of the ship rolling. For the control motion of ship, we can use the right coordinate system. This differs with the left coordinate system due to the coordinate axis is directed on the port side of ship. 12.1.3. The right coordinate system used when side ship rocking. The abscissa x-axis is directed to the bow of the ship. The right axis, y-axis, is to the left side, and the applied z-axis is upward. And the left coordinate system is used when finding elements of the ship controlling motion, different from the direction of the coordinate axis. To the starboard side of the ship for left coordinate system, the abscissa axis, which is directed to the bow, and the applied axis is upward. 12.1.4 positive direction to angular moments of a ship in the right coordinate system. The roll to starboard side, trim to the bow, and positive course change counterclockwise when the view from the above towards the applied axis. Yeah, for the right coordinate system, that is logical. 12.1.5 the elements of ship motion on the surface of water besides of the coordinates of trajectory of the angular moments are the drift angle, which is between the vector velocity and the abscissa axis, the course angle, which is between the longitudinal axis associated with the ship and the abscissa axis of fixed coordinate system, which is maritime navigation, is directed to the north. So yeah, besides of the coordinates, three translational and three angular, we consider some other elements of the ship motion in the coordinates. This could be the drift angle, the velocity vector direction, and the course angle, and the course angle and corresponds with the drift angle and with the velocity angle, velocity vector angle. 12.1.6 the categories of forces when determining the elements of ship rocking. The inertial forces and moments caused by the massiveness of ship and water and proportional to accelerations. The damping forces and moments of resistance of water, the restoring forces and moments that counteract the deviation of ship from the initial equilibrium and return the ship into equilibrium after the cessation of disturbing forces and moments. This is categories of the forces when we consider the ship rocking. And a little bit different, 12.1.7, the categories of forces acting on ship when determining the elements of the controlled motion. The driving forces and moments, this is a force mode on the propulsors and controls. The external forces and moments, which sources are in the aquatic environment, do not have the causal dependence on ship motion, as well as the reactive force and moments from water environment arising by ship motion. So three categories. Another is the driving forces, the external forces, and the reactive forces. 12.1.8. Reactive forces and moments from the water environment arising as a result of ship motion are distributed into internal, that is proportional to acceleration projections, are distributed into inertial, that is proportional to acceleration projections, and viscous proportional to the velocity projections or squares of velocity projections, or into positional forces and moments acting during translational motion and the damping ones during the angular motions, angular rotation. So 12.1.9, differences between two categories of force acting on ship, the projections of which are included in the equation of ship rocking and in the equations of the motion of the ship in water surface. And this means, in second option, equations of the ship motion under controls. What are the differences? The differences are in the classification of the forces category. So, like we told in the 12.1.6 and 12.1.7. 12.1.10, matrix of coefficients of added masses of a ship in water, which elements are proportionality coefficient between the inertial force in moments and the accelerations in each direction, which number correspond to the number of degrees of freedom. Free translation, free angular. So yes, the system of indexes is used. So each coefficient of the inertia of ship in the water, like we say, the added mass or the coefficient of the resistance of ship motion in water, like we say, the damping coefficients. Each of them has two indexes. The first index indicates in what direction the force arises or moment arises. It could be, we can say, the effort arises. In what direction? This is the first index. And the second index means in what direction the motion of ship caused the force of moment rises in the first one index direction. That is the system of the matrix of the coefficients of the added mass is the same as for the damping coefficient, as the same systems of the indexes as for the added masses. Some of the added masses are not masses, some of the added masses are the moments of the inertia. And some of added masses are just some concept intermediate of the mass and the moment of the inertia of the characteristic of the inertia of the water with the ship. It depends on what direction we consider. Is it translational direction? That is the added mass, and angular direction. This is a added moment of inertia. But there could be just something in between. So we can consider the appearance of force in the translational direction under the acceleration and translation direction. But this force caused by the rotation with acceleration in the another one direction. This factor of the proportionality could not be attributed to the added mass of water or just added moment of inertia. It's not so much important, but just that we have to consider this more formal as the factors of the proportionality of the acceleration in definite direction, the translational acceleration or angular, and the force raised in definite one direction. 12.1.11 methods of added masses and moments of inertia finding in hydromechanics. The substitute of ship with the geometric model of a triaxial ellipsoid, which some axes correspond to ship particulars, half of each ship size. Numerical determining of added masses and moments of inertia, and the assumption that ship in the transverse motion is flow around water along the flat cross sections. Yes, this is a subject we do not consider so much, but in the book I indicated originally, there are more details how to find it. This is not the mechanics itself, this is hydromechanics. Maybe we will not go in the deep for this one, sure. But this is the approach how we can find the edit masses. Edit masses we can find due by the fulfillment of the experiment. Edit masses and the damping coefficients of the factors of the proportionality between the ship velocities, translational and angular, and accelerations as well, translational and angular in the water, and the rising forces. To find this, we have to do the, if we have enough opportunities, we have to do the experimental research in the definite tanks with water for researching of the characteristics of ship inertia and resistance in the water. But it could be the numerical method too. The assumptions of this method is assume that we consider the water flow around definite cross sections of the ship case. So we divided the ship case into the cross sections, and assuming that we can consider the ship as a segment of geometric model of triactional ellipsoid, and use the mathematical methods to find the edit masses of the water. This is very complex, and the factors of damping of ship in the water as well. It would be non-linear issue. So this just to have the this question is just to have the outlook of the hydromechanics used for the mechanical research to find the data. 12.1.12. The hypothesis of damping forces to linearization, that is the assumption about linear dependence of projection forces, the moments of resistance on the corresponding projections of translational and angular velocities. In hydromechanics, it's usual to consider the forces of resistance of water proportional to the second power degree in the second of the velocities in the second power 2 second. But if we do that in the equations of the ship motion, the equations will not be linear. They will be second order non-linear differential equations, and they can raise the difficulties of the decision, of analytical decision of non-linear differential equations. So to have the analytical decisions of the equations of the ship motion, we have to assume that for the appropriately small velocities, this this can be assumed that the forces and the moments of resistance are proportional to the squared velocities, but the to linear degree of the velocities. As we remember, the velocities themselves are derivatives of the displacements. So this is the components of the differential equations. Exactly, this impacts on the determination of damping coefficients. So in some other issues, we will consider the decision, the numerical decision of the nonlinear equations, and the approach how to find the factors of nonlinear equations, which we can consider as appropriate to corresponding factors in the linear equations. But it's not for this definite one, but but for this article, we have to just assume that the hypothesis of damping forces is the assumption that linear dependence of projectional forces and moments of resistance on the corresponding projection of translational angular forces are to be used to have the homogeneous linear equations of the ship motion in the water. 12.1.13 matrix, the damping coefficient, that are the indexes of proportionality between the emerging forces and of moments of resistance and the velocities of ship in water, the translational and the angular ones. Yeah, the matrix of damping coefficients looks like the matrix of edit masses with the same system of the indexes. That is the same order of the rows and columns in the matrices. This used to have the matrix form of the equation of the ship motion. Very simple matrix form of the equations. 12.1.14, the system of equations of the ship motion during its rocking, the matrix form equation system, the diagonal form of the matrix of ship internal characteristics, the symmetry of matrices of edit masses and damping coefficients relative to the main diagonal. This symmetry very looks like the symmetry of the matrices of the we probably remember, perhaps we remember that the forces method using for determination of displacements or for decision of statically indefinable mechanical systems. In this method, we use the canonical equations, and for the canonical equations, we had the factors, and the factors are the unit displacements, the displacements of in the definite absent connections when we do the main system out of the assigned statically indefinable system, and these factors we used in the canonical equations are within the matrix, and within the matrix, these factors are of two indexes. One index in what direction we determine the displacement. Second index is on behalf of what effort we consider the displacement in the first index direction. And this matrices of the unit displacement, we say, but actually this is not unit displacement, that is displacement and action of unit forces in the cut-off connections when doing the main system statically definable out from the statically indefinable assigned system mechanical. So, but the system of these displacements and action of unit forces very looks likely as a system of the edit masses in determination of the ship motion equations, and very look like as matrices of the damping coefficients. So each row of the matrix of the edit masses or damping coefficients means the factors to determine the forces arising in definite one direction. Could be one of six directions, as two directions in the Cartesian system of coordinates, translational and three directions translational and three directions rotational. So we have the matrix, and in the motion in each of the direction caused the force arising in the same direction and in all other directions. And that is why we have the matrices of the edit masses factors and the matrices of the damping coefficients, which very looks like, but usually we denote the edit mass as the letter mu, but the damping coefficient as a letter lambda, and the way of use exactly different. So we use the edit masses to the ship acceleration characteristics, sorry, elements, and edit and the damping coefficient matrix we use to the ship velocities in all directions, not the accelerations. 12.1.15 uniformity of equations of ship motion in water with the expanded form of the system of these equations. We probably remember when considering the issue the very big system looking very complex of six equations of the ship motion. There are in the ocean environment, there are considering all the forces of inertia of in each direction we have arising the forces on behalf of the acceleration in all directions to each, and we have the second row in each equation of the damping forces, so forces of resistance arising in each direction on behalf of the velocities in all directions, all six, three translational, three rotational, and we have the third row in the equations of the main types of rocking of the restoring forces, which is only for the main types of rocking. So, and this is uniformity of equations of ship motion in water, and this is expanded form of the system of the equation. The expanded form of the matrix type of the equations. Matrix very simple form, but the expanded form looks very complex. Before the simplification possible for definite assumptions for the main systems of ship rocking, just the vertical rocking, the ship rolling around the abscissa axis longitudinal, and the ship pitching around the transverse axis of the ship trim change. And assuming as well the symmetry of ship. 12.1.16 isolated equations of the main kinds of rocking, heavy roll, and the pitching. These main types of rocking, yes, and we can consider these types of rocking separate when we assume the ship symmetry relative to the diametrical plane and relative to the midship plane. This gives us a great simplification of the expanded form of system of the equations of the ship motion. The separate application of which, the superposition of the main kinds of rocking, is justified by assumption of ship symmetry relative to the diametric plane and the midship section. Diagonal form of matrices of edit masses and damping coefficients for isolated equations of the main kinds of ship rocking in the superposition. And we can reduce the matrix of the edit masses and the matrix of the damping coefficients for the isolated equations, assuming the ship symmetric, because due to this assumption, the inertial forces and forces of the resistance arise only under the action of accelerations and velocities in the same directions of the force. So no other directions of the ship motion for the symmetric ship, no other direction impact on the forces or moments arising in other directions. So we can reduce the indexes from two indexes for the matrices of the edit masses and the edit damping coefficients. First, due to the assumption of symmetry, this matrices reduces to the diagonal form. So all zeros on the diagonal indexes remains for definite magnitudes of the indexes of the edit masses and the damping forces. And next, we can reduce the set of indexes to just only unit one for each type of the rocking, well, generally to each type of ship motion: longitudinal, transverse, vertical, and rolling along the longitudinal axis, along the transverse axis, and along the applied axis vertical. So 6 types we can use to great simplification of the set of the summands of the equations. 12.1.17, the general solutions of isolated linear homogeneous equations for main kinds of ship rocking on calm water. Deciding the general solution, we can find the damping decrement of, after the mathematical transform, decrement of the of ship rocking on the calm water due to the absence of the disturbing forces and moments. The amplitudes depend on the initial conditions, and the phases depend on initial conditions. And the amplitudes reduce gradual due to the damping decrements with the availability of the resistance for the rocking of ship. And we can find the natural frequencies of ship rolling, pitching, and the vertical rocking, considering the ship inertial characteristics and the magnitude of the restoring forces of the ship when deviates from the equilibrium on water. For the main types of rocking, which four we have the restoring forces and moments. Thank you.